In the last two lectures, you have seen the interfacing of the memory with the microprocessor and the interfacing of the I/O devices like the keyboard and the 7-segment LED displays. You can definitely develop a simple system using these devices. But data converters are other important circuits which invariably are to be interfaced with the microprocessors. Now, the digital systems like the one based on microprocessors, they require digital input. And after processing the digital signals, they produce the digital output. So if we have to process the signals through the digital system like the one based on microprocessor, we have to present the signals accordingly and accept the signals in this form. The signals in natural form are continuous normally, and by the use of a transducer, they can be converted into an electrical signal. The signal may be weak, so we condition it, that is, we amplify we filter it, linearize it, and then the analog signal available here, analog electrical signal available here is strong enough. This can be digitized by the use of an A to D converter whose digital output can be read by the digital system like the one based on microprocessor. Microprocessor generates the digital output which can be accepted as such or may be required to be converted back into the analog form for the use of conventional analog devices by the use of an A to D, D to A converter. Then this is our analog output. So this can be the chain. Now we also know that this analog to digital converters and digital to analog converters, they can act as input output circuits to the digital system. So their electrical and timing parameters will have to be matched with that of the microprocessor system. Now we know that the microprocessor based systems are quite powerful. They can interface or they can accept the signals from many sources, not only one but many, like we can see from this diagram. The signals can come from many sources. After this transformation and conditioning, they can be multiplexed through an analog multiplexer onto a single line. This single line is sampled by the sample and hold circuit, which holds a constant analog value at the input of the analog to digital converter. The analog to digital converter converts the signal into the digital form, which can be stored into a port from where the microprocessor based system can use it. In fact, the control signals for the channel selection through the analog multiplexer and the control signal for sampling the analog signal from the multiplexer output and the start of conversion signal from the microprocessor to the A to D converter, and then monitoring of the end of conversion, and finally latching the digital data into the port are all provided by the microprocessor. Now this conserves on the number of chips like digital to analog converter, the sample hold circuits, etc. Now if we similarly see the digital output of the microprocessor can be directed to many these devices. The digital output can be stored by the microprocessor into a port here, and then this digital output of this port is presented to this digital to analog converter, which produces an analog output here. Then through the analog demultiplexer, the analog sample can be directed into one of the channels to which it belongs to. Also, the sample and hold circuit holds that sample of in a particular channel. There can be n channels like this. Then after signal conditioning, the analog signal can be used by the analog devices. So this way we can again conserve on the this D2A converter chips and some other chips by demultiplexing. Now if we come back, we know that the implementation of a converter will determine its performance characteristics like its speed, resolution, compatibility, accuracy, and so on. Our aim here is to see the interfacing of these converters with the microprocessor based systems. So let's take right away the interfacing of a D2A converter with the microprocessor. D2A converter interfacing with the microprocessor. Now in this case, the microprocessor has to write the data through its data bus into a port. Of course, it sends the port enabled signal by address decoding and other control signals. Then this digital sample held in this port is presented to the D2A converter. After giving sufficient conversion time, we can send this analog output to a buffer here. This is a buffer like an operational amplifier, which gives sufficient drive for the analog signal to be used by any device. So we can take the examples of various D2A converter chips to be interfaced with the microprocessor. We know that D2A converter chips are available with the word size of 8 bits to as complex as 20 bits. Most of the applications are covered by the use of 8-bit D2A converter chips. Some other applications are covered by the D2A converters having the word size of up to 16 bits, and very few applications are left beyond that. Anyway, that's too complex a thing. Now let's take the interfacing of an 8-bit D2A converter by taking a practical example. Here we are interfacing a D2A converter, that is 8-bit D2A converter AD558. I am giving the conceptual interfacing. I am not discussing all the pins of a D2A converter chip. Now apart from this D2A converter, the microprocessor provides the address bus. After the address bus drivers and address latch for this demultiplexing, and the data bus drivers provide the sufficient drive on the system bus. So in all these systems, we presume that these control signals MEM-R, MEM-W, IOR, IOW, address and data bus are available to us. So we'll concentrate our discussion on this part. Now this D2A converter has an internal latch. This 8-bit latch accepts 8 bits of the data, that is one sample sent by the microprocessor, when it sends the data to this port through some address decoder, activating the chip select signal and IOW signal. This 8-bit signal is provided to this D2A converter. Then the buffer is also provided within this, so analog signal is available to us. This reference is the power supply reference, which gives an accurate power supply, which should be inherently there in the D2A converter by this taking the drive from the unregulated 15 volts supply. So in this case, we see the interfacing. Let's see the timing requirements of this, or this programming requirements of this. In this case, if we see the caption, the first block is initialize the memory pointer and the sample count. That means here we intend to convert number of digital samples into the analog signals. So we initialize the memory pointer to point to the first sample lying in the memory and the total number of samples to be converted. Next is just to read the sample from the memory and send it to the D to A converter, then wait for the conversion. That means we should know the conversion time, we wait for that much of time, and then we update the memory pointer so that it points to the next location where the next sample is to be picked up. Since we have converted one sample, so the sample count is decremented by 1, and the count is to be checked. If the count reaches down to 0, that means all the samples have been converted, and that's the end of conversion. Otherwise, the process has to be repeated again. So this way, we can see the interfacing of an 8-bit D to A converter with the microprocessor representatively. Now let's take the interfacing of the D to A converter with the higher word size, say up to 16 bits. So in this case, the process remains same, or the technique remains same. Only thing is that we have to have 2 ports. Say there is another port. The microprocessor can write the 2 ports one by one, and the data from the 2 ports is presented to D to A converter simultaneously, and it converts the digital data which has got the word length more than 8 bits, and then of course the analog signal is buffered and sent out. So this is again, the principle remains the same. This is another port to hold the second byte. So if we take the practical example here, again I am concentrating onto the D to A converter. This is the practical example of AD7522, which is a 10-bit D to A converter. So it could be up to 16 bits. So now if we concentrate on this, we see that there are 2 inner ports. One is LSB, another one is MSB. LSB can store 8 data bits. That's the lower 8 data bits of the sample. And the higher 2 data bits of the sample will be stored in MSB. So whenever a conversion is to be carried out, the microprocessor sends the lower 8 bits first and enables this port by sending the enable signal on the LBS line through some port decoding. So first 8 bits have been latched into this LSB port. Then it sends the second sample, which contains only 2 bits, are to be latched into MSB, second port, which is enabled by enabling HBS control signal. Now after the 2 bytes of the data have been latched, then both are simultaneously presented to the DHC by enabling the holding register here through a control signal LDAC. Here incidentally it is connected with the HBS. So simultaneously, as soon as the second byte is latched, the data is presented. And after conversion, of course, the data is to be used by the analog devices. Now if we again go to the monitor, here there's not much of difference between the first and the second requirements. The flowchart is almost similar. Here again we initialize the memory pointer and the sample count as in the previous case. Now we send the lower byte of the sample to D to A converter. Then we send the higher byte of the sample to D to A converter. After sending the 2 bytes, we wait for the conversion. Then we update the memory pointer, maybe by 2, because 2 bytes have been read, and then decrement the sample count to see that 1 sample has been converted. Then we check whether all the samples have been converted or not. If the count is not 0, we repeat the process, otherwise it is just over. So like this, we can see that we can interface the data converters of practically the word length up to 16 bits. This principle can be extended to interface the D to A converters up to 20 bits, of course. So now, after having seen this technique of interfacing D to A converters, let's go on to the interfacing of A to D converters with microprocessor. Again, we know that A to D converters can be interfaced through ports and IOR and IOW control signals. Again, A to D converters also have the this word size of 8 bits, say up to more than say 16 bits, perhaps 18 and 20 bit AD converters are also available, but we restrict ourselves up to 16 bit applications. So in this case, whenever an A to D converter has to be interfaced, we have the analog signal here, presumably supplied by a sample and hold circuit. So this analog signal V in is to be converted. Whenever conversion has to be carried on, now in order to avoid all the confusion about the conversion time, because the implementation of the this A to D converter will determine how much is the conversion time of a sample, and again the value of the sample itself may determine how much time will be taken for the conversion. So blindly, if we try to give the worst case time, then a lot of time is wasted. Instead, we dynamically go on monitoring and just read the data as soon as the conversion is over. Now this can be done by initialization of the conversion. This is an A to D converter. So we just start the conversion by sending a signal like start of conversion. As soon as this control signal goes, A to D converter reads the analog signal and starts the conversion by one of the techniques those could be implemented. Then the end of conversion is monitored by the microprocessor to know when the conversion is over, maybe through some port. This is end of conversion. It can be known by different names like data ready signal, busy bar signals, and so on. But basically, we are looking for whether the conversion is over or not. As soon as the conversion is over, the microprocessor reads the digital sample through the data bus. So that is the simple procedure. But in this case, the handshaking of this ADC with the microprocessor is provided by using different approaches. Like one of the approaches can be status check approach. Now what is the status check approach? What is the status of A to D? That means after the start of conversion has gone, we have to check the status of the A to D converter, whether it's yet carrying out the conversion or it has done the conversion altogether, and we can read the signal. In this case, we take the practical example of interfacing an A to D converter, 8-bit, that is AD570 like this. Now here is the analog input. This has a control signal B and C bar, which requires a pulse width of at least 2 microseconds to start the conversion. This monoshot can provide this 2 microsecond pulse width. This monoshot is triggered by the microprocessor by some port enable signal, whatever the technique that is used. So this monostable starts the conversion. As soon as BC bar of sufficient pulse width is made available to this, DR bar signal, that is data ready bar signal, is deactivated. This goes active, deactivated high, and the microprocessor checks the status of this line through a port, say port 1. Now this is connected to D0. What does the microprocessor do? It says read port 1 and check for this. If it is high, it again continues reading this port and checking its status. As soon as the conversion is over, DR bar signal will go active low. And this is monitored by the microprocessor. As soon as active low signal is determined on D0 line, the microprocessor reads the digital sample through port 2, maybe it's a buffer, into the microprocessor for use. Okay, in this case we have seen that the status is continuously being monitored. Now, in this case we have seen, well, the microprocessor uses very minimal hardware, but at the same time, we are continuously wasting the time of the microprocessor for monitoring DR bar signal. It's not doing any productive work. So we are being penalized in terms of the software overhead. Well, anyway, let's see this software requirements of this through the flow chart. Now, in this case, again, we suppose that we want to convert a certain number of samples, and we want to know where we want to store the samples. The starting address of the memory where the samples are to be stored is initialized. That's the initialized memory pointer, and initialize the sample count, how many samples to be converted. Then start send start of conversion. Then after sending this, monitor dr bar, that is read dr bar and check if it is 0. If it's not, go on doing it, wasting time. Then after this, read the lower byte or read the byte from the output of the A to D converter into the microprocessor. Store it into the memory, update the memory pointer, decrement the sample count. Is the count 0? If it's not, go on repeating the process. If it is 0, that means process is over. Now the next approach for interfacing is the interrupt approach. In this case, the microprocessor initiates the start of conversion. Then it forgets about the conversion and goes on to carry its own job. Now, what is expected is that, sorry, take to the next. That the microprocessor, that A to D converter carries on its conversion, and as soon as the conversion is over, it will generate an interrupting the microprocessor, seeking its attention for reading the sample. That means the microprocessor is being asked to attend to the job for a minimal period of time. Start the conversion, that's all. Then carry on its job. After conversion, just read the sample, that's all. Now, let's take the practical example of interfacing ADC 0801 8-bit microprocessor through this approach. In this case, we have 3 lines, WR bar line, RD bar line, CS bar line, and INTR bar line, apart from 8 data lines. Of course, there is an input analog signal. Now, whenever the conversion has to be started, we say write something into the A to D converter. Whenever we say write and give the appropriate address here, CS bar will be activated low and WR bar will be activated low by IOW bar. As soon as start of conversion indication goes to this A to D converter, it deactivates the INTR line logic high, which after this inverter makes it logic level 0. It can be connected to one of the level interrupts of the microprocessor, like it is connected to RST 6.5 of 8085. Now, in this case, the conversion goes on, microprocessor is carrying on its job. As soon as the conversion is over, INTR bar signal goes active low, and the inverter puts a logic high to RST 5 line. That means it gives an interrupt signal to the microprocessor. If the microprocessor interrupt system is enabled, although we have not discussed the interrupt system as yet in details, but I'll take it to the minimal level. Whenever the interrupt is recognized, the microprocessor will invoke the interrupt service routine to read the digital sample from here and store it into the memory or anywhere. So this is the hardware requirement. Now let's see the software requirement of this. In this case, the interrupt service subroutine that is called, in this case, the microprocessor was carrying on certain job. Now it has to go back to the original job. So in this case, we have to save the status of the microprocessor. That means save its processor status and the registers, whatever are to be used in this routine. Then read and load the memory pointer, because each time now we cannot be holding the memory pointer into the memory. into the microprocessor. So we read the memory pointer into the memory and load it into some register pair, then read the sample, store the sample, and update the memory pointer and save it back into the memory and restore the processor status word and the registers back. And that's the minimal time taken by the microprocessor. Now, this was the interfacing of 8-bit microprocessors, 8-bit A to D converters, sorry, with the microprocessor. This was a third technique, that is ready line. Sorry, I have to discuss this. Ready line. That means control through the ready line. Here we can see that an A to D converter can be interfaced with the ready line. Whenever a sample has to be converted, the microprocessor simply tries to read that digital sample from the A to D converter on these lines. For reading this, it sends the address of the port and IOR, which enables the read and CS bar active low of the A to D converter. As soon as the start of conversion comes, busy bar signal goes active low. This can be connected to the ready terminal of the microprocessor, pulling the microprocessor into not ready state and adding the wait states. This process of adding the wait states goes on till the conversion is over, and as soon as the conversion is over, busy line is deactivated high and ready line is active. The data can be read from here. This is a simple technique only if we are not using ready line for anything else. Then this, the programming is very simple, just one instruction in from this port. Now, as a variation of, or rather the extension of 8-bit microprocessor, this is this extension of the A to D converter, sorry. This is another A to D converter, AD0808, which is to be interfaced with the microprocessor. In addition to the 8-bit conversion, it has an analog multiplexer within this, which can multiplex 8 analog lines IN0 to IN7. Any of the channels can be selected through 3-bit address on these ABC lines sent by the microprocessor. The address is latched into the A to D converter through ALE signal, and the conversion is started by sending us appropriate signal on SOC line, that is start of conversion. Then end of conversion is monitored again, in this case through the status check approach, by another port like this. Whenever the conversion is over, the output of the particular channel is read by the microprocessor through this port. Well, the software requirements of this can be, we have written the software with the view that we take the sample from each of the channels starting from channel 0 to 7. So here, save the processor status word and the registers, load the memory pointer, we understand all this, initialize the channel equal to 0, that means we sample 0th channel, then send the start of conversion, monitor the end of conversion, next 2 blocks, then read the sample byte, store the sample in the memory, update the memory pointer, select the next channel, and go on repeating this process till all the channels have been scanned. So this way we can cover the different 8-bit this A to D converters. Now last, I know that the time is running out, but I'll just take 2 minutes to okay. This is the interfacing of a 10-bit A to D converter, which can be extended up to 16 bits. Now this ADC AD573 is a 10-bit A to D converter. Again, the status check approach has been applied here. We give the start of conversion signal to convert line here. This can be given by setting this flip-flop active high by some port enabled by the microprocessor. When the convert line goes high, that is the indication of start of conversion. As soon as the conversion starts, data ready bar line goes inactive high, which can be applied to the clear point of the flip-flop, thus resetting it back. So convert signal is brought back to the lower level, thus it is start of conversion. Then the microprocessor goes on monitoring the DR bar signal through another port. This is a buffer, single line buffer, through port 1, through one line, and as soon as the conversion is over, this line will go active low, and the microprocessor will start reading 2 bytes of the data. In this case, the lower byte will have only 2 bits, D0 and D1. They can be read by HBE bar active. That means port 3 enable signal will activate port 2, and this enable signal will activate LBE bar signal, which will allow D0 and D1 to be read through this buffer. This is OR signal gate here, so this will be 2 bits will be read. Then after then the microprocessor enables port 3, which enables HBE bar signal, which allows the next 8 bits D2 to D9 to be read through the buffer, again enabled by this. So like this, this A to D converter up to the width of 16 bits can be interfaced. In this case, the software requirements remain the same as that of the 8-bit AD converter, except that each time the microprocessor has to read 2 bytes instead of single byte. I think with this, I am able to give you enough background of interfacing of the D2A and A to D converters with the microprocessor. I hope with this knowledge you will be able to extend it a little more to use these chips for the practical systems to be developed. Thank you very much.